Hi, good morning. Hope everybody is staying well. Okay, well, this is exciting because we're getting down toward the end. One of the nice things about being in the education business is that at the end of the year you have a break and then you come back fresh at the start of a new semester. And we're coming to that end, so that's always kind of a fun part. So, in particular, here we're going to do section 6.5 today, matched pairs, and then going to do section 7.1 soon enough, and then that'll be it. Then in the last week of class, I'm going to give. I'm calling it final exams, but I'm breaking it into a couple of quizzes just to try to make it easier on a person to take. Sort of taking 2 hours, 2.5 hours worth of work is a long time. So I had in mind that shorter periods might help some folks. Okay, anyway, so the material today is also a little easier than some of the other material. Again, we're in a situation where we did the hard work in chapter 3 and chapter 4 of figuring out, making sort of the right mental model of what a confidence interval is, what a hypothesis test is. And then in chapter 6 here, we found ourselves applying that mental model to a number of circumstances. Uh, one proportion, one mean. Difference of two proportions, difference of two means, sort of stuff. And then here we are, last section of the chapter, and it turns out that this section is a repeat of an earlier section in some sense that I'll make clear in just a second. It's called matched pairs, and it comes down to a circumstance that you see an awful lot in practice and that a person can make a mistake on, and so we're cautioning you not to make that mistake. But then once you know not to make that mistake, then the rest is actually just a previous section. Okay, so let's go to that. So I wrote down some data. I'm not going to use the data from the homework this time. I wrote down some data on a sheet. I have 5 people who are in a weight loss study, and there's their before and after numbers. Okay, so almost everybody lost weight. There's this one person here who gained a pound, but almost everybody lost some weight. Now we just saw not too long ago, two means. So a person might be inclined to say to themselves, okay, I'll average all the befores and put that number here. I'll average all the afters and put that number here. This will be my x1 bar. This will be my x2 bar, and then I'll proceed along with a difference of two means type of section. I get that. That's what you should be thinking at this point in our development. But today I want to caution you about something there. If you were to do that, if you were to take the average of all these and put that down, and the average of all these and put that down, you would be throwing away some information. Specifically, you'd be throwing away the information that 180 and 172 are matched. They're connected. They're numbers associated with this single person. And the 120 and 115 are connected. It's not that 120 is a different person than 115 like it would be if you had a treatment and control group. The 120 and the 115 are the same person. So that's to say, the right way to analyze these, the point is that they're matched in big letters, matched, and matched specifically means that the 180 and the 172 are connected. These are not two different sets of averages. They are, in some sense, the average of 5 different things instead of the average of 10 different things. Okay, so because these are matched, M-A-T-C-H-E-D, I spelled that right. Because these are matched, the right thing to do is to just simply do 5 lines here. I'm going to take 180 minus 172 and get, what is that, 8? 124 minus 121 is 3. 165 minus 166, don't miss the negative sign. Or 212 minus 179, oh heck, what is that? 21 and 12 is 33. 33, there we go. And 120 minus 115 is 5. And now I'm going to take the average of this one column of numbers. So I'm taking before minus after. I'm taking the average of that one set of numbers, and that is to say I'm not doing two means, I'm going to do one mean. Because these are matched, I'm going to match them up like I did, and then take the average of one mean. Take the formula for one mean, and of course we've seen that before. Okay, so I'm going to need the mean. I'm going to need x bar, and I'm also going to need s for this data set. And you know me, I'm going to do it on StatKey. No doubt there's some people in the room who are great with a calculator. Good for you. But I'm going to do it on StatKey just because I have it, and it's relatively easy to use. Okay, so I'm doing one variable, so I'm going to go in just a second. I'm going to do test for a single mean. I will, give me a second, but I'm going to do actually here a test for a single mean. But at the moment, I need the x bar and the s, and it's right here on StatKey. So rather than work out some complicated calculator thing, I'm just going to do StatKey. I'm going to edit the data and get rid of all this stuff. And write down my 5 numbers: 8, 3, -1, 33, and 5. And anybody can type a wrong number, but I think I got it right. Okay? And you know, StatKey gives me the dots. We've all seen this many times. It turns out that the mean is 9.60. Writing that down. And the standard deviation is 13.483. Okay, so let me pop that off. 9.60 for x bar, 13.48, sorry about that, 13.483 for s. And I just simply got it from StatKey because I got StatKey and I know how to use it, and so it was convenient. Okay, now I'm going to do a confidence interval and I'm going to do a hypothesis test with a single mean. So confidence interval and hypothesis test using a single mean, and that we've done that before in this chapter. That's section 6.2. It'll involve doing a t-curve and etc. But nonetheless, it's all stuff we've done before. So the only thing that's genuinely new is the observation that if the data is matched in this way, you don't want to do it as two separate sets of data. You want to do it as a single set of data. That's the only thing that's happening here. Okay, so let me get a confidence interval out of this before I throw this piece of paper away. Okay, so for confidence interval, I don't know. What do you think about 90% confidence interval? Just to do something. So of course the formula is x bar plus and minus t star, and again you get it from that page in the book that has all the formulas in one place, and then it's s over radical n. Okay, and we know all these numbers. The x bar was 9.60, the s is 13.483, radical n is not 10, 5, because I have 5 numbers that I'm actually considering. So I'll fill all those in, but I got to get t star. So here I go back to StatKey to get t star. Let's see if I can work this darn thing. StatKey, oh there it is. Okay, I almost lost track of which window I had to open. Okay, so I'm on StatKey, and because I'm doing a single mean, if you remember how you do a single mean, if you flip back to that section, because I'm doing a single mean, I got to do this t-curve thing. Because do you remember that you not only don't know the mean, but you also don't know the standard deviation? Anyway, it's a single mean calls for me to use the t-curve. And degrees of freedom, and you subtract 1 from the number of pieces of data. There are 5 pieces of data, so I enter 4. So again, this is a review. And what did I want? A 90% confidence interval? Okay, so I want to know what constitutes the middle 90, 0.90, enter, and it says 2.132. So to get the middle 90, I need a t of 2.132. Okay, so back I go, 2.132, 2.132, 2.132. And I'll put in the numbers, 13.483, and square root of 5. Plus and minus 9.60, and I'm pretty much done, right? I mean, obviously, I'm gonna punch it out on my calculator, and anybody can make a flub, but we're pretty much done at this point. So again, the big point, not to lose track of what's happening here, is that it looks like there are 10 pieces of data, but there aren't. There really are only 5 pieces of data because the data is matched. You might have before and after numbers in a weight loss. You might have husbands and wives in their opinion of the president. I mean, there's all kinds of things that a person could have. But anyway, if the data is matched one to the other, then you want to leverage the fact that you know that, and work not with two different means, but instead with a single mean. Okay. All right, so time to whip out the calculator and see if I can make it work. This is the hard part for me. Let's see. I got to take 13.483. Oops. See, we got it wrong already. 13.483 divided by square root of 5 equals, and then 6.03 approximately, multiply by 2.132, and I end up with a 12.86. Maybe I'll write that down as an intermediate number. So 12.86. 9.60 plus and minus 12.86. You may have gotten a slightly different number if at some point, with square root of 5, you round it to 2 decimal places. It does not matter. 12.86, add it to 9.60 and subtract it from 9.60. So 9.60 plus 12.86, 22.46. And the low end is 9.60. 9.60 subtract 12.86. Negative 3.26. Negative 3.26. And as always, I'm interested in the meaning of this. What is it that's in there? And of course, what's in there is if you did a census. You made everybody in the world do this diet. Of course, that's crazy. Obviously, that's crazy. But if you did, not 5 people, I don't know why I have so much light all of a sudden. That's no better. Oh, I'd have to click the thing close there. There we go. There we go. So if you did not a sample of size 5, but if you did instead a sample of size 50,000. So you have so much data that surely your numbers are just about spot on. So if you did a tremendous sample and you put 50,000 people on this diet and did before minus after, then you'd know what the true number is. You'd know what mu is. So the mu is in there, not x bar, mu. So if you took 50,000 people before and after numbers, subtracted and got a column of 50,000 weight loss numbers and average those all out, we think that number is in there. And in particular, it's notable, isn't it, that negative numbers are also in there. That is to say, the sample is so small, it's only a sample of size 5, the sample is so small that it's at least conceivable that the whole entire thing is a sampling thing. That in fact, on average, no weight would be lost. So one thing you see, the mathematics tells you that size 5 is not big enough to make very many conclusions. Okay, and of course I'm going to do a hypothesis test. Of course I am. I need a new piece of paper. So just to remind you what the data is, I have 5 numbers. These are basically weight lost. And I calculated the average and the standard deviation, and I'm going to do a hypothesis test. So see how I do. Okay, so my hypotheses are going to be H0 and HA. Okay, and as always with hypotheses, they are not about the x bars, they are instead about the census numbers. So the census numbers here are going to be mu's. So what is mu? Represents weight lost. It's not the before number, it's not the after number, it is the before take away after. It is weight loss. So if we gave this diet to 100,000 people in the world and then took the 100,000 before minus after numbers and averaged them all together, that's mu. Obviously, in a weight loss study, you always have an equals, of course, in H0. In a weight loss study, the argument is about whether you actually lose any weight. Actually lose any weight. Is weight loss greater than 0? That's what you're arguing about in a weight loss study. And let me copy over the x bar and the s just so I can remind myself. X bar is 9.60 and S is 13.483. So the hypothesis test, I hope, we spent so long on it, I really hope it paid off, that the hypothesis test makes sense to a person. We're having an argument about whether, on average, if we gave this weight loss, if we gave this diet to everybody in the world, would the average be zero? That is to say, the diet doesn't do anything, or would the average weight loss be greater than zero? Is what we saw 9.60 just a sampling thing because we did a sample of size 5, or is or is there actually some weight loss and the 9.60 is evidence in favor of that? Okay. Hypothesis test always starts with the same two magic words: assume H naught. Because you assumed H naught, you get a sampling distribution. Happens to be t-curve, but it doesn't actually make any difference to what I'm drawing. It's got a center. Because we assumed H naught says that the center should be 0, because if the true number is 0, then samples should be clustered around 0. Some people will get a little higher than true number, some people get a little lower than true number, samples will be clustered around 0. And furthermore, the mathematics tells you that the spreadedness, we're going to look for S over radical n. 13.483 over radical 5, and I don't know. 13.483 divided by square root of 5 equals 6.03. And if you do 4 decimal places and I did 3, it doesn't matter. It's fine. It's fine. I mean, 2 or 3 decimal places is kind of our standard just because it's enough and not too much. Okay? So now, to calculate the p-value, to find the p-value, we figure out where our sample lies. Remember, it was 9.60? And of course, you can't look up 9.60. You have to instead translate that to its t-value. So t equals 9.60 minus the center, which is 0, over the spreadedness, which is 6.03. And I don't know what calculate that, see what it says. 9.60 divided by 6.03 divided by 6.03 equals, and I got 15.92. No, 1.5, 1.59. That didn't make any sense. 1.59. Okay, and of course I'm going to look up the p-value. In order to look up the p-value, I'm going to go to the stat key t-curve, and I'm going to look up 1.59. I will. But our experience is, we've done a lot of these now, and we know that 1.59 is not big enough. It's not far enough out. In order to be far enough out, I didn't give an alpha, so we're going to take alpha to be 0.5. In order to be far enough out, you have to be like 2-ish. 2.1-ish, 2.2-ish, 2.3-ish. That's what it takes. This is not near 2 or 2.1 or 2.2 or 2.3. So we're not going to make it. We're going to fail to reject. That is to say, this shaded area will be too big. Now I'll ask that key how big it is, and etc. But nonetheless, we know from experience that it's not going to make it. Okay, back I go to stat key. Come on, come to Papa. There we go. But so back I go to stat key, and it's still got the information from the previous. And in fact, because the previous is actually the same, it has a degree of freedom 4 already. So I don't need to dial in a new degree of freedom. Wouldn't be a crime of the century if you did, but anyway, I don't have to. So I'll get rid of the 2 tail, and I'll get a right tail, 1.59. Click on. Am I low enough for a person to see? Yes, plenty low. 1.59. 1.59. 59, okay, and it says 0.94, so between 9 and 10% chance. So the p-value is 0.094. And that's not small enough. That's not below alpha equals 0.05. Take alpha to be 0.05 because that's the number a person most often use, and so when you don't see a number mentioned, 0.05 is what people want. That's not below. So you fail to reject. Okay, so again, I mean, I think this is good news. We're getting to the end of the semester, and I hope that it all, instead of making less and less sense as time goes on, I hope it makes more and more sense. That is to say that the hypothesis test, I hope the argument with a weight loss treatment is weight being lost or not? You've got to use data in order to support that argument, like we talked about on the first day. Statistics is about using data to support arguments. So here's the data. And the argument always goes the same way, so that if a person has got it, then they've got it for good. You assume H naught. That gives you, mathematically, gives you a sampling distribution. It's got a center and a spreadedness. You figure out the p-value. Every one of the things in Chapter 6 has some different little twists, but they're not super big twists. So this one happens to be look it up on a t-curve. So you look up, you figure out what is the standardized value, the t-value, turns out to be 1.59, and then you look it up on a t-curve. The p-value turns out to be not below alpha. You fail to reject. That's like happened in every other problem. Okay, very good. Of course, we're moving down toward the end. We're going to have the usual number of quizzes this week, and then next week we'll have I'm not sure what the right word is for quizzes, final exams. That is to say, the material that I give you for graded work next week will be the final exam that is cumulative. Not just focused on Chapter 6, but focused on all the chapters, including 6, but also including some of the earlier ones. Okay, and then later this week we're going to do Section 7.1, and so that'll be it for the semester. Okay, very good. Bye-bye.